focus. Here we go. So today we're starting a new unit of, it's going to be called trig. We're going to split trig into 2 different units. So this first unit, a lot of it's going to be a review for you guys. And then the next unit will be completely new to you. So we're going to talk about radians, radian degree, and measure of angles. So like I said, page 290 in the pre-calc books where we'll be at. And there's some good notes in that pre-calculus book as well. So you can always refer back to that. So guys, these are how angles are formed. We're starting out really basic. You're going to need to know some vocabulary. You take an initial side, so here's my initial side, and then you open up an angle. That's considered the terminal side. Here's the terminal side, here's the initial side. So we have an initial side, we open up and create an angle. That's the terminal side. So this is just an example of an angle. Oh my heck, I'm not going to be able to focus teaching today if you're all going to talk when I'm teaching, because we have to think. Math isn't easy. So angle in standard position. Here's just a random angle. Here's an angle in standard position. It's just on an XY chart. That's the only difference. So we have our initial side and we open up an angle. There's our terminal side. So just an angle but put in standard position on an XY chart. We have those vocabulary words kind of down. All right, now a positive. Oh, you want me to wait? Okay. Positive angles are created when you go counterclockwise. So here's a clock. Think about a clock going backwards. Counterclockwise, that's in standard position. So we have a standard position, an XY chart here. We're going to be creating angles. And this would be going this way, going counterclockwise. That would create a positive angle. And then to create a negative angle, you'll be in standard position. And then instead of going counterclockwise, if you go clockwise, that creates a negative angle. So see how we're going underneath? That's creating a negative angle. So positive angles and negative angles will be created by counterclockwise and clockwise. Now with angles, so the reason we know this is going this way is those dot, 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 that arrow pointing showing you this angle is created this way. And then this angle was created going up this way. Because if that arrow wasn't there, those blue dotted arrows, we wouldn't know if the angle is created by swooping the terminal side around this way or this way. So those blue arrows we've got to draw. Anytime we're asked to draw an angle, we've got to put in those little dots so you're telling me if I'm going positive or negative. Questions on? Okay, next vocabulary word is called a coterminal angle. So coterminal angles have the same initial side and the same terminal side. So a coterminal angle has the same initial side and same terminal side. So I'm going to let you get that down and then I'm going to show you. Okay, so let's look at example right here. If we have our initial side starting at 0, we open a positive angle of 30 degrees. Coterminal angle will have the same initial side, so we'll start here. And then it's going to go around the circle and end up at the same terminal side. So think about it, you guys. If I start at 30 degrees, aren't I then just going around in a full circle and end up back at that 30 degrees to create a coterminal angle? So we started here at 30, we went around the circle another 360 to get back to here. So what did we do? Didn't we start at 0, add 30, and then add another 360? 390. So a coterminal angle will be 390. If you do 390, you'll end up in that exact same spot as the 30 degrees. So that's an example of a coterminal angle. So of 30 degrees, a coterminal angle would be 390. So think about it. We could go around again. We could do another coterminal angle that's positive. If I'm starting here, if I go around in a full 360 degrees, I'm going to end up back at that same terminal side. So we could take 360 and we could we could take 390 and then add 360 again. So we can just get a bunch of coterminal angles by adding 360. Then it'll put us back in that same spot. Does that make sense, everybody? So let's go the other way. Let's think about it the other way. Wouldn't it still be coterminal to make a negative angle by starting here, going down, around, and stopping there? Wouldn't that put us in the same spot? Yep, so isn't that taking 30 degrees and subtracting 360 to get back to that same spot? Okay, so that's a negative coterminal angle. You took 30 degrees and you subtracted 360 degrees. Does everybody understand how to create a coterminal angle? So that's negative 330 degrees. So that's a negative coterminal angle, and this was a positive coterminal angle. And we could find multiple of these, but that's good enough. So to find a coterminal angle, you will go another full revolution. One revolution is 360 degrees, just so you know vocabulary-wise. So you just take the angle and add 360, and you take the angle and subtract 360, and that's algebraically how you find coterminal angles. Questions on that? Pretty easy. So let's find one positive and one negative coterminal angle. So even though this is not in standard position, these are still angles, still works the same way. So let's find a positive coterminal angle. 120 degrees plus 360, correct? Good. 480 degrees is a coterminal angle. And then we can also take 120 and subtract 360. It'll put us in the same spot. So what will we be at? Yep. So looking at negative 420 degrees, it says find a negative and a positive coterminal angle. So I'm going to think about this here. If I take negative 420 degrees and I add 360 degrees, that'll be negative 60 degrees. Okay, that is true. Is that a negative or a positive coterminal angle? It's a negative. So we've answered, we have a negative coterminal angle. Now we need a positive. So are we gonna, let's add 360 again to that. Isn't that okay? Does everybody understand? So I can add 360 as many times as I want, and those are a bunch of coterminal angles. And I'm taking 60 because that's in the same spot as this, negative 420. We're taking negative 60 degrees, and we're gonna add 360 to that to get us into the positive. Right. So a positive coterminal angle was 300 degrees. Questions on that? Pretty straightforward, right? All right, so in the pre-calculus book, these are the problems. Since you don't have the book right now, we're going to go get them at the end of the hour. I'm giving you what the book is. So do right now, while we're in class, these ones. So I'm going to have you practice now with you. Ready, set, go. All right, so complementary and supplementary angles. Okay, back in we've learned this forever ago. I'll just remind you, two complementary angles, their sum is 90 degrees. Now, this is positive angles. So two positive angles are complementary if they add up to be 90 degrees. So that's a word you'll want to remember because they might say to you on an ACT, these two angles are complements of each other. If one of the angles is this, what's the other angle? So you have to say to yourself, what does complement mean? So once again, complementary means they sum up to be 90 degrees. So if I say to you, what's the complement? It means what makes this add up to be 90 degrees? Does that make sense, everybody? Supplementary angles, the sum of them add up to be 180 degrees. Now that is only two positive angles add up to be 180 degrees. That would make it a supplementary angle. So supplement angles, the sum is 180 degrees. Complementary is 90. So 44A in the pre-calculus book says, if possible, find the complement and supplement of each angle. So let's look at 44A, 3 degrees. So complement, and I'm just going to write C for complement. So the complement angle of this, so this is the algebra you would do, but then we'll just be able to think about it. 3 degrees plus, we don't know, will need to equal 90 degrees. Now solve for x. So x is 87 degrees. So the complement is 87 degrees. Our supplement, algebraically what we're doing is we're saying 3 degrees plus some other degrees needs to equal 180 degrees. That makes it supplementary. So 180 minus 3, right, is 177. So our supplementary angle would be 177 for 3 degrees. Everybody good? That's the complement and supplement. Pretty easy, right? Okay, so can you guys do those ones and finish them up? Okay, awesome. Do that. Okay, everybody. For 44B, what's the complement? 26 degrees, because 26 degrees plus 64 equals 90. Very good. What's the supplement? 116? All right, and that's true because 116 plus 64 equals 180. All right, go to 46A. Is there a complement for 130 degrees?
Negative 40.
-40, so that would be considered not complementary because it has to be two positive angles. Their sum is 90. So this one doesn't have a complement. No complement. Supplement is 50 degrees, correct? That would make it sum up to be 180. So pretty easy. 170 has no complement, correct? It'd have to be a negative to get it back to 90. So we'd have no complement, and our supplement would be 10 degrees. Questions on those? So it's two positive angles. All right, so these are a few more to practice really quick. There you go. The thing is, one way to measure angles is in radians. So guys, you can go from a degree angle to a radians. Radians back to degrees. They are equal, they're just a different form. One's an apple, one's applesauce. So a degree is the measure of the angle. It'll be the measure of our central angle. So degree is the actual measurement of the angle. 30 degrees is the measurement of the angle. Radians would be taking that degrees and switching it into radians would put it into a physical length of the arc that that angle opens up on. So basically, radians is more useful in real world problems because if you're an engineer, you're not going to want to know 30 degrees up is, or 30 degrees of a circle. You're going to want to know the physical amount if you're doing something. So that's why we would want to switch to radians. So I'll say it again. Degrees can be switched to radians, and radians can be switched back to degrees. Degrees is the measure of the angle, and radians will be the physical length of the arc that that angle opens up on. All right, so this is one thing to note. One radian is the measure of the central angle theta that intersects arc S. So here's our arc. Angle theta is opening up on arc S. That is equal in length to the radius. So when this, I'll say that in easier terms. When this arc length is equal in length to the radius, that's considered 1 radian. When the radius opens up and then boom, when it finally hits the same length as the arc, the radius length is the same amount of length as this arc, that's when it's 1 radian. So arc length equals radius when theta equals 1 radian. So maybe write that down. And then this is the length of an arc formula. So S is equal to R times theta. So we can find our length of our arc. S is the length of the arc. And that's equal to our radius times by the angle it opens up on. And that's the angle, the central angle. And we're going to get into more details into that in a little while, and I'll make sense of it in a little while. So right now we're just talking about radians for a second. So I'm going to push pause. Okay, so you might want to draw this down because you will be using this in the book. So everybody pay attention so that this makes sense to you. Because circumference of a circle, so the circumference is the physical distance of it outside of the circle. Circumference of a circle is 2 pi times the radius. Everybody knows that formula. That would give us the physical distance of the outside of the circle. So because circumference of a full circle is 2 pi r, the central angle of one full revolution, the central angle of a full circle, the middle angle, is also going to be equal to 2 pi r. And because that's true, and we know that 2 pi, everybody, I want you to get your calculator. Type in 2 times pi and type it in the pi key. So you'll hit 2 times pi, which we know pi is never ending. They haven't found the end of it. So that's a decimal that goes on forever, but it's just rounding it. So it's approximately, 2 pi is approximately 6.28. So guys, if my radius is 1, the full distance of the outside is 2 pi, which makes sense, right? 2 pi, circumference of a circle, 2 pi times 1, radius of 1. So if we have a radius of 1, the full distance of the outside of the circle is 6.28, and that would be radians. So once again, remember what a radian is. It's when it opens up and finally that arc is equal to the length of the radius. So this circle has about just over 6 radians in the whole circle. So everybody look so that you can see how my radians were made. I start here and I open up, boom, all of a sudden my arc is the same length as the radius. So there's 1 radian. Now I didn't draw this perfectly because I did it by hand, but now I'm going again And boom, now that is the same length as the radius. That creates a second radian. And I go like this and open it again. And now that arc is the same length as my radius, so it creates my third radian. And I keep doing that. So right here is my sixth radian. So that is the sixth radius. And then we're just over a little bit more, puts us back to the beginning. So we have just over 6 radians in a full circle. That's physical units around the circle. So there's just over 6 radius lengths in a full circle. So just maybe write that down, draw the picture, because we're going to use it. So if I say to you, what quadrant is 2.5 radians? What would you say? Where would that fall? The second quadrant, correct? So that's what it's going to be asking you in the book. So guys, think about it. The physical distance of the outside of the circle is 6.28, roughly. And then, like, let's say that so that would be if our radius is 1. So if we had a circle with radius 1, and I said to you, find the entire distance of the outside, you would just say 6.28, and then are we talking centimeters, inches, or whatever unit of measurement? So 6.28 is the physical distance of the outside of the circle. So obviously, if we have a radius other than 1, then we have to multiply that to our radius. Anyways, kind of interesting. Okay, so a couple more things here. So because the radian measure of 1 full revolution, because the measure of a full circle is, because the radian measure of 1 full revolution is, and I meant to write this, is 2 pi. So because the radian measure of 1 full revolution is 2 pi, you can obtain the following. So we know that 1 full revolution is a full way around the circle, that's 2 pi, correct everybody? So let's think about, everybody think, if I said to you only go half a revolution, wouldn't that be this, only the top half? Guys, half a revolution? It's a full revolution, it's a full circle. So think about the math behind that. If we take 2 pi, our full circle, and I only want half of that, that'd be multiplying by a half or dividing by 2, correct? Wouldn't that put me at pi? So then from here to here will put me at pi. So now we know that this is 2 pi and this right here is pi. Now think about it. If I say a full revolution is 2 pi, I only want a fourth of a revolution. That would be taking your 2 pi and dividing it by 4. So algebraically we get pi halves, correct everybody? So that means a fourth of a revolution will put us at pi halves. So here's 1 pi half, right? Isn't this 2 pi halves? Which is pi, right? Isn't this going to be 3 pi halves then? And will this be 4 pi halves, which is 2 pi? All making sense. Okay, good. So let's say I said to you, I want a sixth of a revolution. Not a full revolution, but only a sixth of it. You would take your full revolution, 2 pi, divide it by 6. So that would be pi thirds. So a sixth of a revolution puts us about right here. So that would be at pi thirds. So that's where we have the unit circle come from with radius of 1, and we're going to use that later. Today we're not focusing on that, but I just wanted to show you like where the unit circle comes from. Because we know a full circle is 2 pi, so then we can cut it into a bunch of pieces and get the unit circle. Okay, so quadrant 1. This is quadrant 1, this is quadrant 2, quadrant 3, quadrant 4. So we know this is 0 degrees or 360 degrees, correct? Yeah. So in radians, that would be 2 pi. Didn't we talk about how a full circle is 2 pi? So it'd be either 0 or 2 pi. Now this is 90 degrees right up here. This is 90 degrees, or we talked about that was being also pi halves. This is, if you go right, okay, so let's start at 0. Add 90, that puts us at 180 degrees right here. That's also pi halves plus, not pi halves, but pi halves plus pi halves. That's what I meant to write, which is pi. So this is 180 degrees or pi, correct, everybody? And then think about it. If you add 90 degrees, add 90 more degrees, that puts us at 270 degrees down here. And that's also 3 pi halves. Why? Because here's 1 pi half, 2 pi halves, and then 3 pi halves, 4 pi halves. 4 pi halves, think about what that is. 4 pi halves is 2 pi, so we're at the right spot. So this is 270 degrees, or in radians, that's 3 pi halves. So quadrant 1, won't my degrees be between 0 and 90 in quadrant 1? So would 70 degrees be in quadrant 1? Yes. Okay, quadrant 2 would be degrees greater than 90 but less than 180. So if I said to you, is 100 degrees in quadrant 2, you'd say yes. True? Okay, and then quadrant 3 is degrees that are greater than 180 degrees but less than 270. So it's 260 degrees in quadrant 3. Yes, okay, perfect. And then quadrant 4 is degree measurements greater than 270 but less than 360. So if I said 310 degrees is in quadrant 4, that would be true. Okay, so all of our angles will fall within a quadrant, and then coterminal angles, if we have an angle and then we have a coterminal angle, it'll fall in the exact same spot, so it'll be in the same quadrant. All right, here we go. So 36, this is in the pre-calculus book, it says sketch an angle in standard position. So let's sketch negative 270 degrees. This is going to take a little bit of thinking, but not super bad. So I'm going to draw a terminal side here. We're starting at 0. Now we're going to go negative direction, negative 270 degrees. So let's do it in sections. Let's think in sections, guys. First of all, if we go down, I'll change colors. If we go down to here, won't that be negative 90 degrees? Everybody following me? Now if we go down here and again, that'll be negative 180 degrees. Don't we need to keep going? Yeah. Now, if we add 90 more degrees, won't that put us at negative 270? Does everybody see that? So I would draw in my arrow. And notice my pink arrow is showing that we went in the negative direction. So you've got to draw something so that I know you went in the correct direction. Because isn't the coterminal angle also 90 degrees, positive 90 degrees? Correct. Yeah, so if you don't draw the arrow, maybe you didn't draw it right. Okay, let's do negative 120. Now we're going to just draw rough sketches here if they don't come out perfect like that one. So negative 120. Basically, you're just going to say, where is it roughly? So think about it. Is it from, so I'm going to erase this one. Is everybody okay with that? Okay, let's start again. So negative 120 degrees. So if we start at our terminal side and we go down, won't we be going down? And is it positive? No, it's negative. So down to here would be down 90, correct? Now if we went all the way, that would be at 180. So think about it, guys. Let's do, just so we can get a pretty good sketch, let's do 180 minus 120. 60 degrees, correct? So about how further do I need to go? 30. Not super far, right? Yeah. Okay, so rough sketch is good enough, and then we'll draw that in. So then you would write, it wouldn't hurt to write, that's negative 120 degrees. I didn't draw that perfectly, but rough sketches are good enough. Okay, questions on that? Okay. Okay, you guys do 34. All right, so question for you. A lot of us, so let me give you a trick I use. I don't love sketching negative angles. To me, it's always easier to draw a positive angle. It's just easier to see. So won't a coterminal angle land in the same spot as that? So I always go negative 260 plus 360. That's drawing in 100 degrees. Wasn't that much easier than trying to figure out where negative 260 is? Yeah. So now I know a coterminal angle, so I'm showing you tricks of how to make your life easier. So I added 360 degrees and I got 100. So drawing in 100 degrees should land in the same spot as that. So to me, that's easier. But I need to make sure to draw my arrows this way because we're drawing negative 260 degrees. Does that help a little bit? So anytime you're dealing with a negative, if you want to draw positive, find the coterminal angle. Pretty cool. So this one's an easy one. We're going down barely any, correct? So I'll draw that one in blue. We're going down barely any. And so we draw the arrow like that. Questions, pretty easy. All right. It says find a positive and negative coterminal angle to 7 pi 6. So think about it, guys. If this is 7 pi 6, now if that's just a degree but in a radian instead of degrees. So think about it. If we need to end up in the same spot, can't we just take that and add 360 degrees? Good, we're just going to add 2 pi. Way to remember that. So a full circle is adding 2 pi, so let's keep it in the same form. So a positive angle, coterminal angle would be adding 2 pi, and then a negative would be subtracting 2 pi. So let's get a common denominator. You're going to do this by hand. I want exact answers. So in something like this, you would say that's 2 pi over 1. Common denominator 6. We'd multiply by 6 over 6, correct? So we would have 7 pi 6. I'm going to do it right here. 7 pi 6 plus 12 pi 6. So we're going to have,
19 pi.
yep, 19 pi over 6. That's our positive coterminal angle. Does everybody understand?
Yeah.
We're just doing it in radians now. So let's get a common denominator. We just did it. So we know it's just going to be 7 pi 6 minus 12 pi 6. 7 minus 12. So negative 5 pi 6 would be the coterminal angle. So pretty straightforward. It's just doing a little algebra and using the radian instead of 360 degrees. Because 2 pi is 360 degrees. 2 pi is just the radian, the physical length, and degrees is the measure of the angle. Okay, let's see what time it is. So, now we're going to be able to convert from degrees to radians and radians to degrees. There's benefits to being both. Once again, just a reminder, you can write any degree as a radian. The radian will be the physical distance that the arc is, where the degree is just the measure of the angle. So they are equal, but one's the physical distance of the arc and the other is the angle. So to go from degrees to radians, you're going to multiply the degrees by pi over 180. So, I'll say that again. To go from degrees to radians, you'll take whatever the degree is, you'll multiply by pi over 180. So think about it, guys. We're really just multiplying by a fancy one, because isn't pi the same thing as 180? One's a radian, one's a degree, correct? 180 degrees is halfway around the circle, and pi is halfway around 2 pi. So we're just multiplying by a fancy one and putting it in a different form. So this is a little trick that helps me because a lot of times people will say, well, what goes on top, the pi or 180? Like, I forgot. So here's the trick I use. It's a dumb trick, but it's what I use.
Oh.
From degrees to radians, what did I say second? Radians. So that's what goes on top, is radians. Seriously. From apples to applesauce is on top. So we're going to put the applesauce on top. That's fine. You can think of it like that. Okay. Oh, what you can. I'm just kidding. Okay, so then converting from radians back to degrees. Converting from radians back to degrees. This time we said degrees second, so the degrees go on top. So 180 over pi. We'll put it back from radians back into degrees. I said degrees second, so the degrees goes on top. And then we'd want our radians to cancel out, so this will be in radians. All right, let's do it. Ready to practice? So it should go from radians to degrees goes on top, because I said degrees second. So 180 would go on top. From radians to degrees to, yep. Yeah, exactly. Yeah. Well, so you're saying, wait, so you're saying,
on the top one,
oh yeah.
that's like 1,
Uh-huh.
and the bottom one's 1. Like,
So your degrees will cancel out, and then we'll put it in radians. Yes.
I know the picture.
Okay, yeah, let's hear it.
Who's in chemistry?
Who's in chemistry? Okay. Yeah, absolutely. I mean, absolutely. I thought that was a given. I'm glad Amelia pointed that out to all of you out there. Because, yes, you're right. If we have a pi up here, we need to divide out with our pi. Absolutely. Yes, absolutely. Love it. Thank you, Amelia. Here we go. Convert these to radians. So what I'm saying is, yeah, I know 135 degrees, but what's the length of the arc? Well, let's put it in radians. So let's multiply by, we need the degrees to cancel out, so degrees goes on bottom. So we'll multiply by pi over 180. So now take your, how do we multiply? I'm only going to do this one time, showing you the algebra. We multiply straight across. Otherwise, I'm going to just do it in my head. Isn't this 135 pi over 180? And then you'll simplify. So 135 divided by 80, do it in your calculator, math, enter. I just want it to be quick. I don't care. 135 divided by 180, math, enter. So this is 3 pi fourths. So Guys, 135 degrees would put us at 3 pi fourths.
Over.
Radians. 3 pi. Now this is technically 3 pi fourths radians. 3 pi fourths radians.
Wait, why?
To change it back to a fraction, math, enter, changes it back to a fraction. Okay, negative 270 degrees, what's that in radians? So we'd multiply by pi over 180. So you're literally just going to take negative 270 divided by 180. And you hit in your calculator. Math, enter, negative 3 halves. So that's negative 3 pi half radians. Now guys, this is a math answer. So everybody listen, because some of you are going to go on to be engineers. 3 pi fourths is I'm a math person, so I like that answer. If you're an engineer, they're going to say, I don't like that answer. What is the physical radian? So take 3, type in pi, divided by 4. So that's also 2.356 radians in distance. That would be what the engineer would want. Does that make sense? They wouldn't want it in terms of pi. Mathematicians would, engineers wouldn't, yes? Yep, perfect. Yep, that's exactly what we do. Then consider our radius, multiplying our radius. All right, awesome. Okay, so let's convert these radians back to degrees. Here we go. So we have negative pi half radians. We're going back to radians. We need our radians to cancel out, so we're going to multiply by 180 degrees over pi. So now that would be, our pi's are going to divide out now. Mathematically, those divide out to be 1. So we have negative 180 divided by 2, right? Negative 90 degrees. So if we're at negative pi halves, we're really at negative 90 degrees. Does that make sense, everybody? So sometimes it helps people think about this. If I gave you this and said, graph that, that one's easy to think about, but let's say you weren't quite sure. It'd be easy to convert it to degrees and then graph the degrees. Okay, 9 pi halves, so we're going to multiply by 180 over pi, 180 degrees over pi. Our pi's will then divide out, so we will have 9 times 180 divided by 2. Positive 810 degrees. Yep, and so we have 2 radians. Notice this one's not in terms of pi, but that's okay. These are really just radians, so it's the same exact thing. 9 pi is 9 times pi. It's still a radian. Does that make sense, everybody? It's just, this one's in terms of pi. No, this isn't 2 pi. Good question. This isn't 2 pi. There's a pi in there, but it's already multiplied in. So there wouldn't be 2 pi, though. It's multiplied in. Does that make sense? So like 9 pi is 28.2. Does that make sense? So if this was written as a radian, it'd be 28.3. Okay, so 2 radians. We're still going to multiply by 180 degrees over pi, because technically there's still a pi hidden in here somewhere. Does that make sense, everybody? There's a pi times something giving us that's giving us 2. Anyway, so you just do it the same thing. You'll do 2 times 180. But this time we'll divide by pi to get the degrees. So that's about 114.6 degrees. Questions? Whereas before we didn't have to type the pi in because our pi's divided out. Right here we have to type it in because this has the pi multiplied in. Does that make sense? So then we just divide by pi and it's all okay. Okay, sweet. So you're going to do 47 through 69. Do you want to just keep learning the last part of the lesson, then go get the pre-calc book? Yeah. No, but I want to finish the lesson and then go get the books. Or do you want me to they're written up here. Do you want me to let you do those or not? Keep going then?
Yeah.
Okay. All right, so now we're going to talk about physical length of the arc. So everybody, we just learned how to take something from degrees to radians. That is true. So if you have a central angle and it opens up on an arc, the arc will equal the central angle. We know that. Angle theta, if it's a central angle, equals its intercepted arc. But now think about it, you guys. Think about why this formula is going to make sense. Can't I have this small circle and this big circle and draw a 35-degree angle on them? So if this is 35 degrees, that's a central angle, then this arc equals 35 degrees. That is true. Well, if this is 35 degrees, it's a central angle, so it equals its arc, which is 35 degrees. Well, is it true that that 35 degrees is equal to that 35 degrees in distance? No, so they have different distances. So what's happening here? Well, they have different radiuses, so we've got to consider the radius. Does that make sense, everybody? So the length of this arc, what's 35 degrees in radians? How would we convert that? When we take 35 degrees times by pi over 180. So the physical distance of that arc is, let's do it, 35. So 7 pi 36, right? 7 pi over 36, so that's 7 pi over 36. Now we just said that's the physical distance, but now our radius is different. So let's call this radius 3 and this radius 5. So now we've got to multiply the radius in. So the length of the physical length of that arc is the degree in radians, because that's the physical distance, and then we've got to multiply in the radius. Does everybody understand? So S is equal to radius times theta, where theta needs to be in radians because we're talking physical distance. Anyways, everybody good with that? Okay. So let's read this question. It says a circle has a radius of 4 inches. Find the length of the arc that is intersected by a central angle of 240 degrees. So we say to ourselves, okay, we want a physical distance of the arc. So S is equal to radius times theta. S is the length of the arc. I want actual distance. So our radius is 4 inches, correct? Our theta is 240 degrees. Now think about why this makes sense that we would need to convert the 240 degrees to radians. If we type this in right now, we would be doing 240 times 4. That's 960 degree inches, which 100, that would be like, what the heck, how many inches is that? 960 degree worth of inches. That doesn't make very much sense, correct? You see how right now it's in degrees. So let's convert it. Let's convert 240 to radians. So won't we multiply by pi over 180? Yeah. So I just like to type it into my calculator. So 4 times 240, then divided by 180. So you get 16. We have our pi. So we have 16 pi third inches. Now that's the math answer. An engineer would not want that answer. They would want the actual inches. Like you could actually go out and a sewer pond, calculate, figure out, measure the radius, and figure out the full distance of the outside. Like an engineer would want to know the actual. So type it in, 16 pi, hit enter, divided by 3. So how many actual inches is this? About 16.8 inches, correct? Does everybody see the difference in the answers? Write down both. I like math answers, engineers want that answer. So it's really cool. That's like the actual distance. So it is very applicable in the real world. With what? I would want both answers. If I'm being specific, I'll say leave your answer in terms of pi. If not, I'll say round to the nearest tenth or whatever. If I'm being picky. I practice writing both, but that's just me. Okay. So we just figured out how to find the physical distance of the outside of a circle or of a section of a circle. We did radius times theta. So now we're going to find the area of a sector, which just means the area of a section of a circle. Instead of finding the area of the full circle, we're going to focus on finding the area of just a small section of the circle. So here is the formula. There's 2 formulas you'll see. And they're the same thing. One is just simplified and one's not. So here, let's think about what the formula would be. Isn't this a full circle? So to find the area, what do we do? Pi r squared. Yeah. That'd be the full circle. So now if I say to you, I only want the area of a certain section, wouldn't you say, I want the area, which is pi r squared, and I only want it of this section. So this section out of 360 times by pi r squared. Wouldn't that give us the area of this section? That amount, that theta, out of the full circle is what we want, correct? Does everybody see how that works? So to me, that formula makes sense because I can think of it. Like literally, I haven't ever looked up that formula in years. So I always just say, okay, if I have the area of a full circle, now I just want a section that's the section over the full circle, section over 360 pi r squared. So that is the area of a sector. It's just this little thing means a section of a circle. The section over 360 pi r squared. You'll see it in your book written as this one over here. Theta over 2 times by r squared. Now here's why. What they're doing is they're using this original formula and they're recognizing that 360 is 2 times 180 degrees. Isn't that true? Now look, we have a pi over 180. Those are the same thing. So that leaves me with theta over 2 r squared. So the formula, here's one thing to note. Maybe write both down. I use this formula always. You can use this formula. However, if you use this formula, you need your answer to be converted to radians. If you use this one, you can just plug in the degrees right away. So those are the same thing, just written differently. But one, you would plug in degrees, and the other one, you'd plug in radians. Okay, here's an example. This is literally my last example, and we'll get the pre-calculus book, and the rest of the time will be yours to do your homework. So it says, a sprinkler on a golf course is set to spray water over a distance of 70 feet. So like, I literally pictured this and drew this picture in my head. I said, if I had a sprinkler sitting here and it's squirting out 70 feet, and then doesn't a sprinkler work like this? Like, have you ever seen a sprinkler? Like real life, right? Okay, so it says it rotates to an angle of 120 degrees. So you could literally go out when let's say you get hired by a company and they want to know all these things. You could literally go out, you'll get your little thing, measure the angle, you get a protractor type thing, oh, that's making 120 degrees, so you could calculate all this. Okay, so it says it rotates to an angle of 120 degrees. Find how much grass will be watered. So think about it, guys. The water is and goes down, right? So isn't that just a sector, a section of a circle? Okay, let's do our formula. Area of a sector. I say I want the section out of 360 because I don't want the full circle's area times by pi r squared. Okay, sweet. So area is equal to theta is 120 over 120 degrees out of 360 degrees is what we want the area of. Then pi, our radius, is 70 feet. So 70 feet squared. So now we'll calculate it. 120 divided by 360, then times 70 squared. And the answer would be, the math answer, a mathematician would like the answer 4,900 pi third feet squared, square feet. But an engineer wouldn't like that answer. They would do 5,000.27 square feet. That would be the engineer's answer. That's what you would go with them to. If you went to them and said 4,900 pi over 3 feet squared, they'd say, what are you talking about? And then you'd probably get slapped in the face. So you'd go to them with this answer as an engineer. Does everybody understand? So all this stuff isn't bad, correct? It's pretty easy as long as you know what you're doing. Okay, awesome. Make sure you read the board. So what you're going to do is you're going to come down and get the pre-calculus book. You're going to come back, read the board, and do the problems.